Hi, pre-calculus friends. We're in Chapter 4, and we're looking at polynomial functions. As you glance at this vocabulary, you're going to see that a lot of these terms you have seen before, and some you haven't. So a lot of this will be review, but it'll be review in context. So let's get started. So when we look at the first term, we can see that a polynomial in one variable is pretty much self-explanatory. It is a polynomial with exactly one variable. So for instance, if you look at these sets of functions here, these are polynomial functions in one variable. The A, B, C, D, and E, I should have highlighted that E, all of those are referred to as simply coefficients of the function. So notice that the x is the only variable and this function is based on x. So that's a polynomial, and these are polynomial functions in one equation. So I'm kind of giving you a couple definitions here. A polynomial function is something that can be written in this way. So you notice the descending order. F of x is equal to some value to a fourth power plus some value, or even minus some value to a third power, etc., etc. And we can go on forever. Notice these exponents are whole numbers. X to the fifth power, x to the sixth power, all fine. X to the 1/3 power, that's not cool. So those are polynomials in one variable, and those are polynomial functions. When we talk about the degree of a polynomial, here I have two polynomial expressions, not equations or functions, just expressions. When we have a degree of when we talk about the degree polynomial, what we're going to do is look for the highest degree or the highest exponent, the largest number, I'll say, of variables being clustered together, multiplied together. And in that case, it's 3. So when I look at this polynomial expression, I would say that this is a third degree polynomial expression. And the degree is going to tell us a lot about a polynomial. Right here, we have another polynomial expression, and the greatest degree or the highest number or cluster of variables would be here, where we have 4x's, x to the fourth. Therefore, this is a fourth degree polynomial. The leading coefficient is a term that is going to refer us to the coefficient that is next to the highest degreed term. So the degree of this term is 3, and so the leading coefficient here would be 2, and the leading coefficient here would be -1/3. So as we already discussed, a polynomial function is going to be any kind of a function that we can write in this form, like we talked about up here. So zeros of a polynomial function will be any value that makes this thing 0, particularly any x such that f of x is equal to 0. So that's what zeros of a polynomial would be. So if this is a polynomial function, a polynomial equation would be an equation that you would have with a polynomial, but not without like the y part or the f of x part. So this is a polynomial equation, and you've worked on solving these before, guys. So I know you know how to do this. This is a quadratic. You know how to solve those. So that brings us down to the concept of a root. Now, sometimes we can talk about, or we can always talk about, the root of a polynomial equation. The root of a polynomial equation will be what's going to make our polynomial equation 0. Now, a 0 makes our polynomial function 0, but the root of an equation is going to be what makes our polynomial equation 0. So these values here that make our polynomial equation 0, they can be all kinds of things. They can be real, they can be imaginary, and we'll get to that. But here when we're talking about zeros, we're really talking about, in a physical way, the place on the graph where the function crosses the x-axis, right, where f of x is equal to 0. So these are generally real. Where these can be real or imaginary, it'll make a little bit more sense. Let's get into the idea of imaginary complex numbers and pure imaginary numbers. So I'm going to show you this family tree of numbers that I generally like students to hold on to. All numbers in this family tree can be considered complex. Complex number literally is every number that we've ever thought of, and even some we haven't. So all of those numbers can be in an a plus bi form, where a and b are elements of the reals. And so we know what a real number is. Any number we've ever thought of is a real number. And if A and B are elements of the reals, then there are times when B does not, or when B is equal to 0, and we only see this real number here. And that brings us to our first category, which is real numbers. All the numbers we've ever dealt with are real ones. Now, if there's real, there has to be imaginary. Any number of the form A plus BI is considered imaginary as long as B does not equal 0. Okay, so as long as we have B not equaling 0, that number is imaginary. Now, what does this mean for other subsets of numbers? Let's go ahead and take a look. So on this side, the real side that we're used to, real numbers, again, can be written in the form A plus BI. But here, the imaginary part, that's what that B stands for. The imaginary part is where B is equal to 0. And so given that fact, we know we're basically just dealing with numbers that we're used to. So we break it down into rational, irrational, and we can talk more about what those are. Rational numbers you can write as a fraction, irrational, impossible to do. An example is pi. An example is pretty much anything we've ever dealt with, 3/7. And then we can break down our rationals into integers and all the other things. And you'll see a breakdown of that in your text. What I also want you to keep in mind is that imaginary numbers can also be broken down into a category called pure imaginary numbers. Now, pure imaginary numbers are numbers where the A value of its complexness is equal to 0 and the B value is not. And therefore, you get numbers like 4i or 3/7i or even pi I. So all of these are pure. Let's write that there, pure imaginary numbers. And this is the basic outlook of the family tree. So right now you're asking yourself, what is an imaginary number? And that's what you should be asking yourself. And I'm going to explain it to you like this. So to begin, let's just talk about I. I is equal to the square root of -1. Mathematicians realize that we can't take the square root of -1. However, in calculations, this can be mad helpful to have a value, and so it comes up in some higher level math. But right now, we're just going to define it as I is equal to square root of -1. And this is also part of the definition. I squared is equal to -1. So we get this whole thing that comes out of this idea of what is I to the first power? Well, it's I, or the square root of -1. I to the second power, we just said it's -1. I to the third power, that's going to be, if you think about it, negative I. And then I to the fourth power, if you think about what that is, that's 4 i's being multiplied together. If we know that 2 of them is -1 and the next 2 would be -1, -1 times -1 is 1. This process of going from going from I to -1 to negative I to 1 is a cycle. This is going to be a cycle that you'll see. And what that means is if I move on to I to the fifth power, it'll really be I to the fourth power times I, which then brings us back to, we know I to the fourth power is 1, which brings us back to I. So I to the fifth power starts the cycle over again, and we get I. You can then conclude that I to the sixth is going to be -1, I to the seventh is going to be negative I, and I to the eighth, as in all multiples of 4, when I raise I to the power of any multiple of 4, it will end up being 1, and we can continue that process. Sometimes you'll see problems that will require you to know how to do that. So that is all I want to talk about in terms of the pure imaginary number I, right? Or an imaginary number I. Complex numbers are any numbers that can be written in the form A plus BI, as we talked about before. So a complex number would be 3 plus 2i, or 0 minus 4i, or just negative 4i. All of these are considered complex numbers, as is 10 plus 0i, which we would know it as just the real number 10. Now, pure imaginary numbers, we mentioned before, they're imaginary numbers that only have the imaginary part. So as I said before, pi I, 4/7 I, etc. Now, this is our last vocabulary term. It is called the fundamental theorem of algebra. And the way I would describe that is using the textbook's definition, which is here: every polynomial equation with degree that is greater than 0 has at least one root in the set of complex numbers. So we know what a complex number is, and what they're saying is that anytime you have some kind of an equation, some kind of a polynomial equation, and we're looking for a root. Remember, root is where the equation is going to equal 0. If we find that root, at least one of them has to be in the complex numbers. And it's almost like, yeah, I guess that totally makes sense because all numbers are complex numbers. Then we have the corollary here. The corollary to the fundamental theorem of algebra. Sorry if I said calculus last time. The corollary of the fundamental theorem of algebra basically states that the degree of the polynomial indicates the number of possible roots of the polynomial. So knowing that degree, in this case, depending on how many factors here, that would tell me the degree. That's the number of possible roots to that equation, or possible places where our equation can equal 0. It will make sense as we move on with the examples. So here in this image, what we're doing is kind of thinking through a little bit about those theorems. So here, this is degree 1, and you notice the degree 1 has 1 0. You can definitely have 1 0. And with a degree 2, you can have as many as 2 zeros. There are ways to have less than that, like if I had the parabola floating up here and stuff like that. Degree 3, we can have 3 zeros. Degree 4, you see them. 1, 2, 3, 4 zeros right there. And here's a degree 5 where we have these changes and we have some zeros here, 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 and here. So what I want you to see is that there's also other ways of this happening. So when I have a degree 3, notice that there's really no possible way for me not to have an x-intercept. Degree 3, like all other odd degrees, right? If you think about odd degrees, here's an odd degree, here's an odd degree, and here's an odd degree. And this one too, and of course this one. These odd degrees always have to pass through the x-axis. No matter how you draw them, they always have to pass through the x-axis. They must have at least one x-intercept. Whereas even degree polynomials, these guys here, may not have that situation. Notice this guy, yeah, it passes through 2 times, even though it's a 4th degree. But this one over here passes through not at all, and it is a 4th degree as well. And we talked about this floating parabola at the top. Okay, so with all of that, let's go ahead and take a look at this first example. This first example is one that's going to be referencing some information from the beginning of the chapter, so let's start there. Many grandparents invest in the stock market for their grandchildren's college fund. 18 years ago, Della Brooks purchased $1,000 worth of merchandising stock at the birth of her grandchild, Owen. 10 years ago, she purchased $500 worth of transportation stock, and 5 years ago, she purchased $250 worth of technology stock. The stock will be used to help pay for Owen's college education. If the stocks appreciate at an average annual rate of 12.25%, determine the current value of the college fund. So we will do that in this question here. Now, part A asks us to write a function in one variable that models the value of the college fund for any rate of return. So we're going to start off with this function down here. So the money in reference to is going to be based on x in this case, which is going to be based on, as they ask for us to do, any rate of return. So why this value? Why does it look like this? Let's talk about it. So x to the 18th power is indicative of the fact that for 18 years, $1,000 will be in the bank. And what's happening, for those 18 years, what's happening is that every year, in a sense, the bank will multiply the amount of money by a factor that's going to refer to the interest amount. So if the interest in this case, which we're going to see, is 12%, the bank could multiply it by 0.1225, but 1.1225, where's the 1 coming from? I'll explain that. That 1 is referencing the fact that we want the original amount plus this interest amount of 12.25%. And that's how we'd write it. So that's what X is referring to. But this happens not just once, but this happens over and over again. Every year, this money is being multiplied again and again by this amount. And so how many years is this happening? This is happening for 18 years. And so whatever the rate is, whether it was 12.25 or something else, the bank is going to constantly multiply that amount by multiply 1,000 for 18 years by the interest rate. And so that's why we get 1,000x to the 18th power, and then we get the following values of 500 times x to the 10th, as that was purchased 10 years prior, and $250 times x to the 5th power, as that was purchased 5 years prior. So now let's go ahead and use that information to do part B. Part B says use this function to determine the current value of the college fund for an average annual rate of 12.25. So as discussed earlier, we know we're basically finding the value of this function at 1.1225, right? And so you get where that came from. So what we're going to do is really just plug that information in. I don't know about you, but I am not interested in doing this by hand. It would take forever. So with the help of a calculator, we find that this value of the amount of money that Grandma saved for Owen is going to be somewhere close to $10,038. So here an example to a little bit less strenuous. We're just being asked to figure out a couple things about this polynomial function. So state the degree and lead coefficient of the polynomial function. You guys can all see that the degree is 3 and the lead coefficient would be 1. And so now we'll look to determine whether 4 is a 0 for the function. So you remember, if 4 is a 0, when we plug 4 into the equation or into this function, we should see if we get 0, right? If the value of y is going to be 0. So with a little bit of calculation, 4 to the 3rd power is 64. This over here is going to be, what is that, minus 96 plus 40 and minus 8. When I join some well, not like terms together, but terms with the same sign. So this is 104 and this is negative 104. And so what we see is that, yes, indeed, 4 is a 0. Here in example 3, we are being asked to do something we haven't done before. So we're going to write a polynomial equation of least degree with these roots. Now we remember roots are what makes the polynomial equation equal to 0. So basically I have 0 is equal to, watch this, x minus 2, because that would definitely, 2 would make it 0. And then x minus, this is going to look weird, 4i, and then x plus 4i. We never factor down to the I situation. In fact, once we get to a place where things don't look right, we often say we can't factor, but sometimes if we were to factor, we can get down to I. It'll make sense later. We'll talk about it, I promise. But to find the polynomial equation that this is true, we're going to multiply all of this together. Here's what I want you to remember. Do you remember that a plus b times a minus b is equal to a squared minus b squared? Right? An old fact from Algebra 1 or at least Algebra 2. You've seen this relationship. Well, a plus bi times a minus bi, these are called conjugate pairs, by the way. Or are they called conjugate pairs? They're pairs. I think they are conjugate pairs. Anyway, when we foil this together, we're going to get a similar situation. Let's use this as a framework. If a plus b times a minus b is a squared minus b squared, then this has to be a squared minus bi quantity squared. Take a moment to breathe. Hopefully that makes sense. And then following along, we get a squared, that looks like a 9. We get a squared minus b squared I squared. What did we say I squared was? Do you guys remember? -1. So this is a squared minus b squared times -1. Hopefully you're with me when you see that the answer is a squared plus b squared. So here's the rule I want you to now know. We just proved it. We showed it. Now we know it. A times bi, a plus bi times a minus bi will always get us a squared plus b squared. And you remember, I don't know if you were taught this, but a squared plus b squared was always told to you guys. I know I tell my students this. in lower, classes that's unfactorable. But technically, it's unfactorable over the reals, but it's not unfactorable over the imaginary numbers. How is this going to help us with the problem? Well, we have this situation here. So instead of going through some weird process, I'm just going to say, oh, this is x minus 2. And over here, we end up with x squared plus 4 squared. You see that? Therefore, I can say this is x squared plus 4 squared, or I can say that basically what this is x minus 2 times x squared plus 16. And now this is short work to just multiply all this together to get my polynomial equation. And so my final equation, I know this took a little bit longer than we wanted it to, but that's okay. We get x to the third power plus 16x minus 2x squared, and that's going to be a minus 32. And so if I join some like terms together and put it in descending order, this is what I have. All right. So that was only part A. Let's go to part B. So part B is asking us a very interesting question. It says, does the equation have an odd or even degree? Well, clearly it's odd, right? How many times does the graph of the related function cross the x-axis? Well, let's go ahead and find out. So here it is. I grabbed this from Desmos. I plugged it in. I grabbed this graph. And basically, we see that to answer this question, how many times does the graph of the related function, which is this, cross the x-axis? It's one time. How do we jive this? We've got 3 roots, 1, 2, 3, but it only crosses one time. Well, you remember we talked a little bit about that earlier. There's a real root, but these guys are imaginary. When we have imaginary new roots, they do not represent true zeros in our function. All right, so here in example 4, we are asked to state the number of complex roots of this equation. So what we're seeing is that we have a degree 4, therefore there should be 4 complex roots according to that fundamental theorem of algebra and its corollary. Then find the roots and graph the related function. How are we going to find roots here? The question should be a little like, what are we doing? So basically, to find a root, we're going to solve this equation. So when we solve this equation here, seeing that it's set equal to 0, the only way that we solve higher order polynomial things like this is that we're going to factor. And I don't know if you remember factoring, guys, but it's a useful thing to have in mind. So what we're doing is trying to find 2 numbers that multiply. Basically, 2 numbers that are going to be placed here and here that are going to multiply to give us 9x to the 4th power, 2 numbers here and here that are going to multiply to give us 4, and then hopefully when we multiply the inner 2 and the outer 2 and we find the sum, we're going to get negative 35. If that sounds confusing, then we need to have a talk about factoring, which is totally okay, but it's a skill that we're going to need to have. And so when I'm looking at this, I see 9 and 4 and I see 35, and I know 9 times 4 is 36. So in my brain, I'm like, all right, 9x, and let's put a 4 here because I know these guys will be multiplied together. But 9x times what gives me 9x to the 2nd power times what is going to give me 9x to the 4th? Just x to the 2nd power. And 4 times what is going to give me 4? Just 1. Let me get my signs correct. So I know that this has to be a negative 4, but I also want a negative 35. So if I make this 4 negative, a positive 1 times a negative 4 is going to be a negative 4. So that's cool. But more importantly, I get a positive 1x squared here, and here I get a negative 36x squared. And so that's how I get my negative 35x squared. So I'm feeling really good about the way that I factored that, about the way that I handled it. And then so now they want us to know, then find the roots and graph the related equation. Okay, so we've got to find the roots and we've got to find the related equation. But first we need to factor this out completely. So I can continue factoring this to x plus 2 times x minus 2. But the next thing for me to consider is how to factor that part over there, how to factor the 9x squared plus 1. So I could see if there's some way for me to use that a squared plus b squared can be factored into a plus bi times a minus bi. But if that's a little bit too esoteric, if that's weird, what we can do is just say, well, you know, we set each of the factors equal to 0 anyway. And if this 9x squared plus 1 is a factor, set it equal to 0. And that's how you're going to find the solution to this polynomial equation. So let's start there. 9x squared plus 1 is equal to 0. To solve this, I'm going to throw the 1 over to the other side. And so I get 9x squared is equal to negative 1. And then x squared is equal to negative 1 over 9. You see it. We are going to get I. So we need to take the square root of x squared to get x. And we take the square root of negative 1/9. And that's going to leave us with x is equal to the square root of this, but we're going to rock a plus or minus because we know that x could have been positive or negative before we squared it in order to get this value. Hopefully that makes sense. All right, so now I'm going to break this down a little bit further. So I get plus or minus the square root of negative 1 is I, and the square root of 9 is 3. So plus or minus I over 3. So those are two possible roots that we have, or two answers to this. And then the other two are pretty obvious. X is equal to negative 2 and x is equal to 2. So what this tells me, since these guys are imaginary, those are not real roots, so they're not going to affect my graph. Let me go run over to Desmos and show you what the graph will look like. So remember, we were graphing the related function here, which is y, or f of x, whatever, is equal to 9x. I don't know why I lost that. Minus 35x squared minus 4, and this is what we get. Here's a real 0, here's a real 0, and there's only imaginary zeros left. Therefore, we only have 2. So that's what the relationship between the zeros and the roots of our polynomial equations and functions are. So here's example 5. A meteorologist sends a temperature probe on a small weather rocket through a cloud layer. The launch pad for the rocket is 2 feet off the ground. The height of the rocket after launching is modeled by this equation here. Notice this is a polynomial equation. Oftentimes when you're dealing with physics and you're dealing with the motion of a thrown object, you will see an equation that's similar to this when we're dealing with feet per second. A little bit different when we're dealing with something, when we're dealing with meters per second, but we'll talk about that more later. So the height of the rocket after launching is modeled by this equation, and where h is the height of the rocket in feet and t is the time elapsed in second. So when will the rocket be 114 feet above the ground? So we want the height to be 114 feet. So simply, we start off by putting 114 right in for the height. And then we need to figure out the time when this will happen. So now we're going to solve for t. The first thing I like to do when solving for any of these types of polynomial equations is to set it equal to 0. So notice I move the 114 over to the other side, and we end up with a negative 12 or a negative 112. So when solving anything like this, we're going to try to factor. So notice I factored out the GCF, the greatest common factor. And so now this looks a little bit, oops, I think I got a sign wrong. Now what this looks like, this should be a minus since I factored out a negative 8. Now this looks like something that I could factor. And so, again, here's our factoring skills coming into play. And I know 2 times 14 is going to be 28, 1 less than this. So I'm hoping to be able to add a 1 to that. I don't know if that makes sense, but it will in a second. So we're going to put the 14 here, and 2 times 14 is 28. I want that to be a negative 28. So I also want to add a, interesting, this should be a plus sign because when I factored out the negative, okay, so I want this to be a negative and I want this to be a negative 1 because negative 1 times negative 14 is going to give me a positive. These two multiplied together will give me a negative 1t. This will give me a negative 28t, and this time I'm adding them together to get me a negative 29t. Let's talk. There's other little methods of factoring, but I'm trying to do this quickly so the video is not superiorly long. So we got this is equal to 0, and now what we need to do is set each of the factors equal to 0. And so if that's equal to 0 and that's equal to 0, when I do that, I get that t is equal to 14. So that happens at 14 seconds, and then t could also be equal to 1.5 seconds, right? So 1/2 second. Time 1/2 second. So the next thing we're going to do is verify this using a graph. So I'm happy to go to Desmos to do so. So when we look at Desmos, we see that we have a verification of the 2 values where x is time. So we get 0.5 and we get 14 seconds as the time when the rocket will be at that particular height. All right, I hope that made sense. I look forward to chatting with you soon. Let me know if there's any way that I can help. Take care.